Hey everyone, and welcome to this explainer. Okay, today we are going to completely demystify a topic that literally strikes fear into the hearts of calculus students everywhere: choosing the right method for finding volumes of revolution. We are taking all the guesswork out of this and giving you a bulletproof visual strategy to tackle absolutely any problem your textbook throws at you. Seriously, you'll never have to blindly guess again. Look at this quote from a Reddit user, asking for a guide because they're just so confused by disk versus washer versus shell. Honestly, if you have ever felt exactly like this, you are so far from alone. Students all over the globe freeze up when faced with these problems. You've got a bounding curve, an axis of revolution, and suddenly you have to pick between three completely different mathematical tools. And making the wrong choice, it feels like you're trapped in an impossible maze of algebra. But don't worry, we've got you covered. Today, we're running through the method dilemma, visual shape cues, the golden mnemonics, integral optimization, a step-by-step guide, and finally, the ultimate secret. Section 1, the method dilemma. You know, students often memorize the formulas perfectly, but then hit a total brick wall trying to actually decide which one to use on a test. So we've got these three primary tools, right? The disk method, the washer method, and the shell method. Textbooks kind of make it seem like you have to magically intuit which rigid path to walk down for a specific shape. But as we're going to see, the math itself actually doesn't lock you into just one path at all. Section 2, visual shape cues. This is where we shift our focus away from those dry equations and get right into pure geometry. When you face one of these volume problems, don't just stare at the functions. Stop for a second, evaluate your axis of revolution, and really imagine that two-dimensional area sweeping through three-dimensional space, drawing a solid shape in one full, continuous rotation. I mean, think about it. If you spin a flat rectangle around one of its edges, boom, you get a solid cylinder. Spin a right triangle around its vertical edge, perfect cone. You really just need to ask yourself what the physical object actually looks like. You've got to let the physical shape guide your method. Does your rotated solid look like a compact disk? Like, is it totally solid with its base flush against the axis, zero gaps? If so, you're looking at the disk method, for sure. But if your shape has a gap, like empty space in the middle, it's going to look like a CD with a hole punched out. That empty gap is basically screaming at you to use the washer method. And this is absolutely brilliant. It perfectly shows how even a really complex, continuous shape like a sphere is mathematically just an infinite stack of flat, super thin disks. They're sliced right perpendicular to the axis, gradually changing in size from small to large and back again. Visualizing these geometric slices and how they stack up is the absolute key to unlocking these problems. Section 3, the golden mnemonics. All right, let's move to a massive turning point that is going to permanently lock these alignment rules into your brain. Okay, the crucial point here is this totally brilliant mnemonic, para-shell. When you draw your little representative slice in your 2D region, check its orientation. If the long side of that geometric slice runs completely parallel to your axis of rotation, you must think para-shell. A parallel slice means the shell method is your absolute go-to. And conversely, we have perpendicular. If your rectangular slice cuts directly straight across your rotation axis at a 90-degree angle, it is definitively perpendicular. And that demands the disk method, or the washer method if it has that gap we just talked about. Parashell and perpendicular. Seriously, if you just say them aloud during your exam, you will never mess up the setup again. Section 4, integral optimization. Here is where we level you up and embrace the lazy mathematician approach to save you some serious time. Okay, there's this massive myth that only one specific method will mathematically work for any given problem. Absolutely false. Since both methods actually describe the exact same volume of space, technically, you can always use either the shell method or the dishwasher method. It's totally just a question of strategy and asking yourself which calculation is going to be easier to solve. Let's look at integral complexity. Sometimes setting up your problem relative to the x-axis means you have to split your shape into two regions, because the top curve literally changes halfway through. And that means you're forced to calculate the sum of two separate, completely ugly integrals. No thank you. The absolute best strategy is to take like 30 seconds to briefly sketch out both the dx and dy setups. Then embrace your inner lazy mathematician and simply pick the option with the fewest parts to integrate. Section 5, your step-by-step guide. Let's pull everything we've talked about into a foolproof 4-step action plan. Step 1, draw the graph, shade the region, and draw a dashed line for your axis of rotation. Step 2, Evaluate your slice direction. Is it parashell or perpendicular? Step 3, mentally check both your dx and dy setups. Will one of them trap you into multiple integrals? And step 4, choose the path of least resistance. Pick the one integral method. Rely on this visual algorithm, and you are golden. Section 6, the ultimate secret. We're almost done, but we've got one final conceptual hurdle about the absolute limits of these formulas.
So you might be wondering, hey, if both methods theoretically describe the exact same volume, can I just pick my favorite, like the shell method, and literally use it for every single problem? Well, technically yes, but practically, it is a terrible idea. Forcing a shell method onto a shape that is just begging for a disk method might trap you in crazy advanced integration techniques you haven't even learned yet. Flexibility is your true superpower here. True calculus mastery isn't forcing a formula, it's choosing the path of least resistance. And by mastering this visual intuition, you've completely conquered solids of revolution. But it kind of leaves us with a wild final thought. We've just solved all these shapes that spin perfectly around an axis. But how on earth do we calculate the volumes of chaotic, completely irregular shapes, like a mountain or a human heart, that have zero symmetry and defy rotation entirely? I'll leave you to chew on that one. Thanks for joining me on this explainer, and keep visualizing.